Hello! Welcome to my talk on 3D printing and composite parts, and how we can use 3D printing to create custom composites inexpensively at home. There are essentially three different basic approaches to using 3D printing to create composite parts for rocketry. The first is to directly print with a composite-infused filament, the most common being carbon fiber-infused nylon, though other common 3D printing thermoplastics can also be used, including PLA, PETG, and polycarbonate. This has the advantage of being relatively approachable, though it really is only going to produce 3D printed parts with slightly different mechanical properties. Notably, composite filaments often have better bridging and overhang characteristics, as well as less warping while printing. The final parts will also be more rigid than the standard plastic, with a slightly higher temperature resistance as well. However, the filament is a lot more expensive. It requires a wear-resistant nozzle to print, and the final parts can actually have slightly worse layer adhesion than standard plastics. The second way to use 3D prints to produce composite parts for rocketry is to embed lengths of composite tow into the part as it is printing. Machines that can do this start in the tens of thousands of dollars, and the resulting parts still have a lot of the weaknesses of traditional 3D printing. These machines are well outside the scope of this talk, but should at least get a mention. I've mentioned it. Consider them mentioned. The third way to produce composite parts with 3D printing is to combine a traditional composite manufacturing technique with a 3D print. And this will be the focus of the bulk of this presentation. I'll be discussing three different ways of doing this: compression molding, vacuum bagging, and a wet layup and heat shrink over a 3D printed mandrel. In front of me here, I have a few examples of composite parts, molds, and most of the various equipment we're going to need for the different processes I'll be demonstrating today. Here I have a motor retainer printed in a carbon-reinforced polycarbonate, which prevents melting and deforming when exposed to the heat of a burning motor. This here is an example of a 3D printed mold for a vacuum bagging process, which I'll be using to produce a fin can later on. Over here, I have a couple different examples of compression molded composite parts, including this complex interstage for a two-stage project. This fin was actually compression molded with a three-part printed mold, which I have part of here, and the interstage used probably my favorite technique that I'll be demonstrating today, a dissolvable compression mold. Here's another example of one of those that I'll be using later on. Lastly, this full version of the two-stage interstage features a section in the middle here, which was formed with fiberglass sleeves heat shrunk over a printed mandrel, which I have an example of right here. Now, let's talk in a bit more detail about how we go about 3D printing molds and mandrels. Welcome to Fusion 360. This isn't going to be an extensive CAD tutorial. I'll just be demonstrating my process for mold and mandrel creation with some comments on general rules of thumb. I'm starting here by modeling the solid composite tip of a nose cone. I would always recommend designing the final part you want first and then designing the mold around it, rather than trying to directly design the mold itself. For this part, I'm going to be using a dissolvable compression mold, which will allow me to have undercuts without any visible seams on the final part. The other advantage of a dissolvable mold is that I don't need to worry about mold preparation, mold release, and design elements like draft angles and separation features. For the three-part fin mold I showed earlier, I did have to include a chamfer between the two main faces of the mold to allow me to separate the mold and remove the final part. One important feature you will need, regardless of mold style, is a straight or nearly straight section where the two pieces of the mold can be compressed together. This will allow the chopped carbon tow to fully consolidate inside the mold, as well as force out any excess epoxy that you may have needed. Now, moving on to the mandrel for the main body of the nose cone, the process is much the same, though this mold will require some form of surface preparation to allow it to be removed once the part has cured. I would really recommend some sort of a physical separation layer if possible. Balloons work well for oddly shaped parts like this. It is, of course, still possible to do a dissolvable mandrel, which would allow you to make things like a single piece honest drawn nose cone using this same technique. One thing to note about these sorts of nose cone molds is that they can very quickly become much taller than most 3D printers can print. This can be solved by splitting them apart into multiple pieces and keying them together in some way. Here I'm using a simple dowel pin style keying feature, but in the past I have also used threaded extensions and holes to attach parts together. One thing I'm doing wrong here is putting the male end of the dowel on the top section of the mandrel. If I put it on the bottom section, it would be much easier to print, only needing some bridging over the top of the hole on the upper section. Finally, we can talk about vacuum bagging molds. Just like with the mandrel method that we just discussed, a vacuum bagged part like this will only really have a defined dimension on one side. In this case, the controlled dimensions are going to be on the outside, as that will allow for the fin can to be more easily integrated into the rest of the rocket. Because we're going to be 3D printing this mold, there's no reason not to include features like a boat tail, beveled fins, and large integrated fillets. In fact, as we'll see when we go to slice these parts later, compound curves like this can actually give slightly better surface finishes, since the layer lines won't be as consistent and stair-steppy. Now, for the mold itself, we're going to be modeling it to produce one section of the fin can, from the tip of one fin over to the tip of the next. The 3 or 4 sections can then be epoxied together to create the full part. The biggest advantage of this is that the fins are physically the same part as the boat tail, greatly improving its strength. I'm going to be using a simple clothes storage bag for this process. This won't give me as much of a vacuum as a proper vacuum bag setup, or even something like a food saver, but it's hard to argue with the price, and it will still help to improve the fiber consolidation and the fiber to resin ratio. Now that we've finished designing our molds, we can jump into the slicer and start talking about special considerations for printing. First, materials. For a dissolvable mold, you're going to need to use a filament that readily dissolves in a common solvent. Some options for that include PVA, which dissolves in water, PVB, which dissolves in isopropyl alcohol, and ABS or ASA, which both dissolve in acetone. There are also more exotic options like HIPS in limonene, but we're going to stick with more common solvents. I use ABS or ASA for my dissolvable molds since acetone won't attack the fully cured composite part, and it's less than half the price of PVA. It's also a lot more commonly available than PVB. For reusable molds, the clear winner in my eyes is PETG. It's affordable, easy to print, and doesn't readily bond with epoxy, so demolding is usually a lot easier. Print settings are also pretty straightforward, though this is a case where you really do want the lowest layer height your printer can achieve before print quality starts suffering. For me, that's 0.1 millimeters. Also, you want these parts to be strong, but there's no need to crank up the infill percentage. A reasonable 15 to 25% infill is just fine. If you need more strength, especially for the compression molds, increase the number of walls and the number of top and bottom layers, since those will do a lot more to improve the overall strength of your part. Another trick to cut down on printing time: you don't need to be printing your infill at 0.1 millimeters. Prusa Slicer has a setting called Combine Infill, and it allows you to set your infill layer height to be some multiple of your perimeter layer height. With 0.1 millimeter layers, combining infill every 2 layers means that the infill itself is being printed at the perfectly reasonable and typical 0.2 millimeters. Big molds like this will take a long time to print, so it will actually make a significant difference in your print times to optimize the infill in this way. Once we slice the part, notice how obvious the layer lines are on this coupler section, and how they look much nicer and less jagged on the boat tail. This is that advantage of compound curves I was talking about earlier. This isn't meant to be a deep dive into 3D printing and slicing for rocketry stuff. There are plenty of other tutorials out there that explain that in a lot more detail. So let's get back to the composites work. All right, so welcome to the unscripted part of this, where we're going to actually be creating some composite parts. We're going to start with the compression molding of the tip of the composite nose cone we're going to be making. So this is a dissolvable compression mold made in ASA, and it's going to be what we're going to be using for making the tip. To start off, a couple of general safety / cleanliness things. Would really highly recommend that you put something down on your work surface, like this disposable tablecloth, or heck, even a trash bag or something like that, just to protect the surface, because you will inevitably get epoxy on whatever it is that you're doing, and inevitably one of the little tiny pieces of chopped toe will get stuck to that epoxy, and then you will have a piece of chopped carbon fiber toe stuck to your workbench forever. So cover your surfaces with something, and then, as always when working with epoxy, gloves are pretty much mandatory, because you don't want to get the epoxy on your hands because you can develop allergies, and you also don't want to accidentally get carbon fiber embedded into your skin. That can be incredibly painful. To start, it's important to note that what we're targeting is a final carbon fiber density of about 1.8 grams per cubic centimeter, and we're looking for about a 60-40 fiber to resin ratio, which means that for every cubic centimeter of volume of your final part, you want about 1.08 grams of chopped toe. I've already measured out the amount for this part. And then you're gonna need an excess of epoxy. Usually I tend to go with about the same amount as the amount of chopped toe. And when we do the actual compression, that will force out the excess epoxy. And that's another reason why you want to have this, is because when you force out that excess epoxy, it will drip everywhere. You'll notice that this clamp is covered with epoxy already because it's solely used for this. So I used this scale already to weigh out the chopped carbon toe, and because the scale is honestly not super great, I am going to actually be measuring out the epoxy with these syringes, which I find to be quite helpful as well. As for the epoxy, it's important to note you want to be using a really thin epoxy, because it needs to be able to be forced out of the mold as the mold is being closed, and thicker epoxies will have more trouble with that. So something like, this US Composites laminating resin, West Systems, any sort of laminating resin, really thin laminating resin, will tend to do well for that. If you use something too thick, you'll have trouble getting the mold closed, and you won't get a great finished part. The other thing to note about any of this stuff is that if you're using an epoxy that sets at an elevated that needs an elevated temperature cure, you're going to need to make sure that your molds can handle that elevated temperature. All right, cut for a bit. I'll be back. I need to clean this out. Well, we're back. The camera battery died, and since we only get one shot at this, we're gonna have to make do with whatever got recorded prior to this. So, quick summary, compression mold, generally speaking, you want to go a little bit of fiber, a little bit of resin, a little bit of fiber, a little bit of resin. You don't want to pre-combine everything all at once because you will get a massive unruly blob. But sometimes what I like to do is to just combine a little bit of fiber with a little bit of resin, especially for small molds like this where it can be tricky to get stuff into the mold closure. It can be helpful to pre-combine a little bit of stuff before putting it into the mold. Again, this process is more of an art than a science, and you'll figure out your own favorite way of loading all of the fiber and epoxy into the mold. And as long as it's all in there and wetted out, and you've made sure you get it in all the little cracks and crevices of the part, the exact method of getting it in there is not a huge deal, just because everything will consolidate when you do in the compression process. The other thing to note is that you want the longest cure time on the epoxy that you can get, just because this process, especially for larger molds, can be time consuming. So long cure and again thin epoxies are your friend. This is probably a bit too much pre-mixed stuff. As you can see, it's becoming a bit of an unruly blob. Probably should have done less, but let's see if we can make it work. Is the last of it. So once we get this in, we can start actually compressing the mold. I probably should have put a slightly longer lead in on the compression side for this. That can help with getting everything loaded, because again, you're not going to get it's not going to all fit at first because you have to compress it to get it all to fit. And also we have excess epoxy. Okay, we're back. I've gone ahead and I've gotten almost all of the fibers into the mold, and I've gotten a fresh set of gloves because the old ones were just completely covered in epoxy and carbon. And you can see that we do have the mold closing. And so now all we need to do is clamp it, which is what this clamp is for. We can go ahead and start clamping it. One important thing about this is that you probably will need to progressively clamp these parts, these molds, to get everything to consolidate properly, which can take a few minutes. You want to tighten it a little bit, let the epoxy work its way out, tighten it a little bit more, There we go. You can see now we're getting out all that excess epoxy that I was talking about. And, all right. Now, we just get to wait for the epoxy to set. All right, so we're back. Hopefully that compression mold section didn't go too terribly. I haven't looked at it yet. But now it's on to the rest of the nose cone form. So I've gone ahead and already put a party balloon over this nose cone mold. You can see it's a little bit not quite fully stretched onto the mold here at the top, but that should be taken care of just fine once we put our reinforcement over it. And as for the reinforcement, I currently have it set up to do 5 layers. We're going to do 3 layers of fiberglass and 2 layers of Kevlar alternating. So it'll be fiberglass, Kevlar, fiberglass, Kevlar, fiberglass. That's basically it before we get started. The reason we're going with fiberglass and Kevlar here is because carbon fiber will block RF, and if you want to put a tracker in the nose cone, that means you need to be using not carbon fiber. So I'm going with fiberglass for strength and Kevlar for a bit of added impact resistance. One thing to keep in mind when dealing with Kevlar, though, is you want to make sure that you are using dedicated Kevlar shears, because it can be a real pain to cut. So do make sure you're using dedicated Kevlar shears for your Kevlar. The other trick for doing this that I want to make sure that I mention is chip brushes. I know a lot of people will say like squeegees or something like that. Squeegees don't work so well on curved surfaces. So I have found that chip brushes do a good job of getting the material wetted out without way oversaturating your fibers. All right, and away we go. I'm using the same epoxy for, I'm going to be using the same epoxy for all of these demos today, just because it's what I've got out right now, and it'll work well for all of them, because it's a nice laminating epoxy. All right. So the other thing to note is, in general, with these sorts of projects, you want to have the epoxy forced up through your fabric from below. You don't want to try and force epoxy into the fabric, because that way you minimize the amount of air bubbles you could trap. If you're trying to push stuff down into the fibers and into the mold, you're going to introduce a bunch of air bubbles. So we are going to start by putting a fairly thick coat of epoxy directly onto our prepped mold. Before we even put any fiber down, we're just gonna lather this up with a bunch of epoxy. All right, I think I've got that pretty thoroughly wetted out. So let's get our first layer of reinforcement on here. So this is, I don't know if I've mentioned it, This is a fiberglass sleeve, so I'm not going to have to deal with any seams, like if I were to be wrapping this with a fiberglass cloth, which you could also do, but then you have to deal with seams. Come on. There we go. Open that up. And slide it down. Okay, so it turns out that this camera has a 10-minute recording limit, which means I have to go quickly. As you can see, I have already gone ahead and gotten all 5 layers of the reinforcement in place, and I have the heat shrink tube cut to length already, and then I have my heat gun. The one thing I will say is that for something like this, where it's changing diameters pretty drastically, I might recommend going with a heat shrink tape instead of multiple different sizes of heat shrink tube like I'm doing, just because it will be significantly easier to get everything shrunk properly. So this is going to be a bit of a challenge. So I'm going to start with this thinner heat shrink tube on the top. Push it down, and then I'm going to take off one glove to use the heat gun to heat shrink it into place. This is something you have to be careful with because it is very easy to go too far in the shrinking process and accidentally blow a hole in your heat shrink. I'm starting up at the top here so that I can shrink this down all the way and then work my way down the nose cone so it doesn't start pulling this thinner heat shrink on the thicker section too far back up the nose cone. So it's, again, we have these very varied diameters. Again, you want to be careful with this because if you overheat it, you will punch a hole through your heat shrink. I've done that many times before. There is a simple solution, heat shrink it again, but that can be a bit annoying to have to do. Alright. That is pretty good for that layer, I think. I'm going to try and shrink this up a little bit more up there. And then I can set the heat gun down, turn it off. And move to the larger diameter heat shrink. So what I'm going to do is I want to make sure that this larger diameter heat shrink is actually going to overlap over where the smaller diameter heat shrink is, so that we actually do get to heat shrink the entire nose cone. And we'll do that this time. Come on. Let's go. Obviously, this stuff can be a little bit tricky to apply sometimes. And here I'm going to actually start down at the bottom so that I can just get everything shrunk. So I can get a side where it's shrunk down onto the whole surface of the nose cone, because that'll allow me to just that'll give me a little bit more breathing room when it comes to positioning this. And then slowly again working my way up the heat shrink. And yeah, you will get sort of bubbly bits like this as it's partially shrunk, but if you just lightly get a little bit more heat, it'll shrink a bit further and those will go away. But at first it's kind of an inevitable fact of the process. The other thing to be careful about with this process is that you want to make sure that you don't actually... I mean, you'll end up blowing through the heat shrink long before this comes up, but you want to make sure that you don't overheat the mandrel underneath to the point of melting it. Though again, you will blow through the heat shrink long before that becomes a concern. So a quick trick, if you realize too late that the two sizes of heat shrink you got are not quite enough, you can spiral cut one of those pieces of heat shrink and use that as a makeshift tape. Alright, welcome back. Now we're going to move on to vacuum bagging. In front of me here I have our vacuum bagging mold for our fin can. This is one of 3 we need to make a full fin can, because this is going to be a 3-fin rocket, unlike the one that we designed earlier. So I'm not sure how well it comes across on camera, but it has one fin here, and then the boat tail in the middle, and a section of coupler up at the top. I have gone ahead and already cut two layers of 3K 2x2 carbon twill, which is going to be what our reinforcement layer is, what our reinforcement is going to be. And then I've also gone ahead and prepared some perforated release film and some breather fabric for the vacuum bagging process. So now we're going to go ahead and start mixing up some epoxy, and we're going to use the same trick as before with the chip brush to try and get as little epoxy as enough epoxy in there, but no more than we need, because we want to make sure that we're not using we don't want to use excess epoxy to the point where the vacuum bagging process itself becomes difficult. All right, I'm going to cut here for a sec. Alright, so while I'm mixing the epoxy, I guess one thing to note is this table has become a complete mess. So this is an example of why you want to be making sure that you are covering your work surface with something that you can just ball up and throw away when you're done. Because there's just so much epoxy just everywhere on this table, from both the compression molding and from the wet layup and heat shrink, that it's really no fun. So before we get started, I do want to note again just that we are going to want to make sure that we're driving the epoxy up through our reinforcement fabric rather than trying to drive it down, because that'll introduce air bubbles. It's not as big of a deal here with vacuum bagging as it is with our other processes, but it's still something just to keep in mind. And I will also note that I have done some preparation to this surface. It's been sanded and sealed and stuff. So once again, just starting by just getting some epoxy down on this surface with our chip brush. Okay. Now that we're happy with the amount of epoxy that we've pre-applied to our mold, we can go ahead and start applying our first layer of fabric. The other thing I will note, just as a piece of advice, is when you're cutting out carbon fiber fabric or fiberglass fabric, it can often be useful to tape out the lines and then do the cut so that you don't end up with a bunch of frayed ends on your fabric. So we're going to go ahead and just lay this across our mold and go ahead and push it down. Again, we're going to be using this stippling action to make sure that we don't move the fibers around too much. And you might need a little bit of extra epoxy on your brush just because it tends to absorb a bunch of stuff. And you want to make sure that we are wetting out the entirety of the fabric. This 3K 2x2 twill will conform to the surface of the mold pretty readily. Actually, even more so than the tape is actually what's causing the biggest issues here with regards to getting it to stay in place. But the fabric itself will conform to the mold quite easily. You want to make sure that the tape is only on the outside of the area that you're going to actually be using of the part, because that where the tape is, we're not going to get a good bond on this on anything but the top layer. So what I'm just doing right now is I'm feeling through the fabric to make sure that there isn't part of the mold surface that we need underneath it where the tape is. Being careful again we don't want to be brushing this epoxy onto the fabric because that will move it around. That will move around the toes within there and we won't get as even of a finish. The other thing to note is that that's especially important on this very first layer here because this is going to be the cosmetic layer that's exposed on the outside of your final part. So this is the most important layer to get right because it's going to be the cosmetic layer that everyone will see. So we're going to go ahead and add just a bit more epoxy to our part here so that we have a bit of excess for when we put our second ply down. Now that we've gone and gotten this first layer down, we can go ahead and get started with our second layer. Again, we're just applying this in basically the same way as we did the first. Trying to drive the epoxy up through our laminate rather than down into it so that we can make sure that we don't have any air bubbles where we don't want them. That's why I made sure to put a bunch of excess epoxy down on that layer before we started with this next layer so that we could drive that excess epoxy up into this layer. And you can do this either with the brush or just by hand like I'm doing here. The one downside of using a PETG mold like this is that the epoxy really doesn't want to stick to it. So this stuff is lifting up underneath my hands as I'm going, which is not ideal. Again, I'm feeling around just to make sure that the edges of where the actual part is are fully saturated with epoxy. And then I'm just going to do one last bit of stippling with this brush. There we go. So that's the 2 layers of carbon fabric done. Now for the release film, it's the same thing. We just set it on top, push it down against the part, and you can see the epoxy already starting to come through that surface there, and that's going to get absorbed by that breather fabric, which is the last layer that we're going to be putting on. You know, I guess I never mentioned why you might want to do this. The advantage of this over traditional methods of creating a fin can are that the biggest advantage is just that you're able to remove a bunch of the unnecessary material that you otherwise don't need, but would take up a bunch of valuable weight in your final part. Since we're able to make this without, like, you could do tip to tip carbon over just a standard airframe, but this is effectively tip to tip carbon without the standard airframe underneath. Okay, so now we have our vacuum bag. This is just one of those clothes bags. This is just, literally, it's just a clothes bag that we're going to be using for this one. And we want to open it up. Okay, there we go. And then once it's in there, we want to make sure that everything is still in place. And then seal it up and draw a vacuum. And I'm actually going to take this slightly off camera to go draw the vacuum. There we go. Final bagged part. The one thing I forgot to mention is you do want to make sure that your breather fabric extends to be underneath where the port in your vacuum bag is, because otherwise you're not going to be able to actually draw the air out of this breather fabric. So I've added a small extension here that comes down to the port. All right. Now we just wait for everything to set. And now, thanks to the magic of video editing, all of our parts have finished curing. We're going to start with our compression molded part, which we can take out of the clamp now. And the important thing to note here is that while we now have the part in here, we need to get it out of this mold. So what I have here is a small container of acetone, and we can just deposit this into the said container of acetone. And normally what you could do is you could literally just leave this here for several hours, and eventually all of the mold would dissolve. But I'm lazy, so what I'm going to do is instead use this clamp to at least crack open. There we go. The mold a little bit, so that the acetone can more easily get in. And this will go a lot faster. There. And now, just do that. And now it won't take nearly as long. So I'm going to set that aside for a bit, wait for it to finish, and we can move on to the next part, which is our nose cone here. So if you recall, we had the issue with the not having quite the right size heat shrink here, so I made some jury rig heat shrink tape. And we can start by removing that. Set that aside. And then we can use our pair of scissors here to start cutting away the heat shrink. And then now that we've got it started, we can just unwrap it. And you'll notice we didn't get quite as good of a finish on our jury rigged heat shrink tape as we did on the rest of the nose cone, but that is something that can just be solved with a little bit of epoxy after the fact. So now to remove the mold, we're going to need to cut off all of our excess here at the top and the bottom, and then we can push the mold out from this side. But I'm going to set this aside so we can get the vacuum bagged part out. All right, let's see how the vacuum bagging turned out. And we're going to need to pull back our separation layer. Okay. Now that we've pulled that off, we can see where we had excess epoxy. It's all stuck together. Now we just need to get it out of the mold, and I think that should be fairly easy with this one because we have these big wide areas down here where we can just sort of pull it up and away from it. There we go. And as you can see, we have the boat tail here, the two fins, transition, and now we just need to cut out all of the parts that we want. Do this 2 more times and glue them all together. All right, and now we can go back to our compression molded tip here. It's only been a few minutes and you can see already that, yep, it's just completely falling apart. This is a rather messy process, as is all of this stuff with composites. But it's hard to argue with the results. Set that back in the acetone for a few minutes just to get any bit more stuff dissolved. Okay, so a couple of final thoughts on the parts. I've gone ahead and trimmed the frayed edges off of the nose cone, so it's now ready to accept a tip and a piece of coupler. The nose cone tip has been cleaned off with some more acetone and water to get all of the remaining plastic off, and it's ready to be bonded in. And for our fin can piece, it turns out that the bag that I was using didn't actually hold a particularly good vacuum, which is why we have these spots here where it's lifted up off of the mold. So just make sure when you're doing this that you're using a vacuum bag that actually does a good job of holding a vacuum, because if it doesn't hold the vacuum, the part can pull away from the from it. But we do still have a nice surface down here on the bottom for binding. So if I find a use for this, it may actually still be useful. So I think that concludes everything I wanted to make sure to address in this presentation. If you have any questions, feel free to leave them in the comments. Thanks.